We will continue from the previous video. From the previous video, you learned that the shape of the phase diagram of a binary system that is made of completely miscible elements A and B will be lenticular in shape. As we reduce the temperature, the system will turn from a complete liquid phase to a mixture of liquid and solid phase, and eventually to a complete solid phase. We also mentioned that when the solid and the liquid phase are coexisting, the composition of each phase is different from the nominal composition. Then how can we get the exact composition for the liquid and the solid phases? Let's look at one example. Construct a binary phase diagram. Assume the composition is 50% A and 50% B. Let's start from a very high temperature, say T1. At T1, there's only one phase that is liquid, and the composition of the liquid is 50% A and 50% B, which is equal to the nominal composition. Let's decrease the temperature to T2, where T2 lies on the liquidus line. At T2, infinitesimal amount of A-rich solid starts to form. I'm sorry that I made a mistake in the notes. It's not pure A, it's actually A-rich solid phase. The liquid phase will be slightly B-rich. Let's further decrease the temperature to T3. At this temperature, we have substantial amount of the liquid phase and the solid phase. The liquid phase is element B-rich, and the solid phase is element A-rich, compared to the nominal composition. Note that as the temperature decreases, although the liquid phase will be always B-rich and the solid phase will be always A-rich, the liquid phase will become more and more B-rich, and the solid phase will become less and less A-rich. As the temperature further decreases, the solid phase will eventually become 50% A and 50% B, being consistent with the nominal composition. Moreover, as the temperature decreases, the content of the solid phase increases and the content of the liquid phase decreases, which is quite intuitive. How to quantify that, we'll see that in a sec. Further decreasing the temperature to T4, it will just follow what we have just described. On the solidus line, we have infinitesimal amount of liquid remaining, and the liquid phase is B-rich. The solid phase now approaches 50% A and 50% B. When we further decreasing the temperature to T5, everything is solid. The composition is pretty straightforward, just simply 50% A and 50% B. Out of the above 5 temperatures, you can tell T3 is the most interesting. At T3, you have two phases, liquid and solid. From the phase diagram, you can read off the compositions of the solid and the liquid phases, and to use the Lever rule to calculate the mass fractions of the solid and the liquid phases. For convenience, we'll copy and paste this phase diagram on a new page. We'll label a new temperature called T6, which in the liquid and the solid zone. The first question is, what is the chemistry of the solid phase at T6? From T6, we'll draw a horizontal line and let it cross the solidus line. Then read the composition corresponding to the solid phase. Here it's roughly 10% B, and from this we can tell the composition of the solid phase is 10% B and 90% A. The second question is, what is the chemistry of the liquid phase at T6? Again, you draw a horizontal line, but this time it crosses the liquidus line, and you can read the composition, which is 60% B. So what we have here for the liquid phase is 60% B and 40% A. You can see that in both cases, the liquid phase and the solid phase, they don't have the nominal composition. The third question is, what is the mass fractions of the liquid and the solid phases at T6? To solve this problem, we'll use the Lever rule. The line segment from the composition to where it intersects with the solidus line, let's call that L. The line segment on the right from the composition to the crossing of the liquidus line, let's call that S. Note that the L is not on the liquid side, but on the solid side. The S is not on the solid side, but on the liquid side. It's like a lever. When you press down on one end, the other end pops up. Hence, it is called the lever rule. The mass fraction of the solid phase is simply S divided by S plus L. The length of the segment for S is simply 60% minus 50%. The length of S plus L is simply 60% minus 10%. The rest is easy. That's just simply 10% divided by 50%. You get 20%. You have 20% mass fraction of the solid phase. For the mass fraction of the liquid phase, it's just L divided by S plus L. L is 50% minus 10%, and S plus L is 60% minus 10%. You have 40% divided by 50%, that gives you 80%. Then the mass fractions of the solid and the liquid phases adding together gives you 100%. In this example here, since T6 is not too far away from T2 on the liquidus line, qualitatively we know that we only have a small amount of solid phase forming and large amount of liquid phase remaining. Indeed, by applying the lever rule, we can calculate that the solid phase in this condition is only 20% mass fraction. In this and the previous videos, we only looked at the Gibbs free energy and the phase diagrams of the completely soluble systems. In the next video, we'll move into systems that has a limited solubility of the two constituents.